Welcome. Today we will be taking a look at the notes worksheet entitled Domain and Range, two very important characteristics when dealing with the concept of functions. So we'll look at them just strictly algebraically and then also using some of the technology as well there. So make sure you please do have a graphing calculator handy. So why don't we start it out? It looks like just a few examples today, and hopefully we'll kind of solidify some of those ideas as we go through that process. So example 1, everybody, at the top should say something like solve for the domain algebraically. And I guess we should go over really what domain represents and then jump into letter A there. But remember the idea. Domain represents all of the numbers that you can put in place of x that will produce a real number answer. So they are the inputs of the function. So remember how functions are defined, everybody. Something goes into the function rules tell us what to do to that input. The function manipulates it essentially, and then out comes an output. And so what we want to know is all the values that can go into the function that will produce a real number output. Okay, well let's get started. It looks like A, B, and C kind of go hand in hand here. So let's go ahead and take a look at each of those and see where it leads. So anyway, it looks like I'm trying to find the numbers that I can put in place of x, essentially. What values would go in the input where I would take the square root of x and produce a real number answer. Well, just to kind of get this going along a little bit here, I'm hoping everybody does realize that I can put in positives for x. So I can take the square root of a positive number in the real number system. I can put in 0 for x because I can do the square root of 0. But I run into issues when I try to put a negative in for x, because I can't do the square root of -1. I can't do the square root of -2 in the real number system. And so as a result, it looks like the values for our input have to be either 0 or positive. And so we can express our domains in something along these lines right up here. X is greater than or equal to 0. Okay, good. So the values you can put in place of x that will produce a real number answer. Letter B, let's jump right into that one. Same family of functions, what's called the square root family. And so in this case, again, I do have that issue. Whatever is underneath this root cannot be negative. It must be greater than or equal to 0. So in terms of formalizing this up a little bit and getting this moving along for us, I mean, this is basically what I know when dealing with the square root. Whatever is under the root has to be positive or 0. And so when I sort of look at it in those terms, then I can go ahead and figure out what the inputs have to be. Everybody, if you don't mind, go ahead and subtract 3 on both sides there. And it looks like when you subtract that 3, I should get something like this. And it's always a good idea, maybe check a couple answers there. I'm saying that our inputs have to be bigger than -3 or equal to -3. And so try it out. If I put -2 in there, yeah, that's going to be fine. If I put -1 in there, yeah, that's going to be fine. If I try to put -4 in there, -4 plus 3 is -1, and I cannot take the square root of -1 in the real number system. Okay, good. Let's do part C. So function h, defined by this right here. I would actually encourage you to pause the video for a moment. I'll get you going on it, but I'd ask you to come up with the domain when all's said and done. I'm curious if you happen to remember something about this one. So in this case, I see that as the situation at hand here. When dealing with this particular family of functions, that seems to be the case. The expression under the root has to be greater than or equal to 0. Well, solve for x if you don't mind there for a sec. All right, well, let's see how you did. I'm going to just sort of take a look up here, see if I can pull this off. But basically, I would subtract 8 on both sides. So I get -2x. And then greater than or equal to -8, and then I would divide by -2, and -8 divided by -2 is 4. I'm curious if you happen to remember something about inequalities here. That's why I put this one in place. In this case, when I divide by -2 in an inequality, I do have to change the symbol. So just wondering if you remembered that piece. But basically, I see that as our domain. Anything less than 4 or equivalent to 4 would work. Nothing greater than 4 would. Okay, good. So square root family goes nicely. It looks like I have a quick question dealing with that one, so why don't we take care of that before jumping into the next family of functions. So it says on your paper, when determining the domain of a square root function, what do we know about the expression under the root? And I'll just write it like this. It must be greater than or equal to 0. All right, perfect. So that expression, whatever it may be, cannot be negative. All right, let's see if we can dive into D, and then E, and then F. So different family of functions, what are called the rational functions. And so different conditions apply with these functions. Let's see if we can figure it out. So I have function P here is equivalent to taking the number 2 and dividing by our input. And so let's see what's going on here. Can I put in just a normal positive number? Sure. Can I put in a negative number? Yeah, of course. 2 divided by negative 1, 2 divided by negative 2. Certainly. I can divide by a negative number. Can divide by a fraction. That would be fine. We have algebraic rules that allow us to do that. There is only one dilemma that I see, one restriction. And I think we kind of all know this to be the case, but I simply, in a fraction, cannot divide by 0. And if my input is 0, that would make me numerically divide by 0, which unfortunately just doesn't work. Okay, good. So we cannot have 0 in the denominator of a fraction. And so that seems to be our restriction with this particular family of functions. All right, so let's go into function Q then. I've got 4x on top and x plus 5 down on the bottom. And in this particular case, I would sort of just envision it something like this. So that x plus 5, I know, cannot be equal to 0. And so if I can think about what would make it equal 0, that's going to be excluded from the domain. And so I hope everyone would agree here, just the way I set this up. You would probably go ahead and subtract 5 on both sides, and you get x can't equal negative 5. Okay, and if I put negative 5 back in, I'd get 4 times negative 5 on top, which is negative 20, but I do have negative 5 plus 5 on the bottom, which is 0, and I can't do negative 20 divided by 0. Simply does not work. All right, good. 2 domains down. Let's take care of letter F with this particular family. And so I have a function r here, x minus 1 over x squared plus 1. And in this case, again, I would sort of think about it at least in these terms. So that's what I'm looking for. Really, that denominator can't be 0. And I would go ahead and subtract 1 on both sides. And sorry, I'm going to come up here and kind of work this out a little bit. But I would get x squared can't be negative 1. And then if I sort of undo this square right here, kind of like this and like this, I end up getting x can't be equal to I or negative I. But hey, when we're talking about functions, we probably should be very clear about this. When we're talking about functions, we're really only talking about the real number system. So this has no bearing whatsoever on the domain of our function. And so in reality, it doesn't seem like there are any real numbers that are being excluded here. And so as a result, we're good. And this is all real numbers. We can put any number in for x and get an answer. So sorry if there was some confusion along these lines, but as soon as I kind of see that it's only imaginary numbers that would make the denominator 0, real numbers have no bearings on that, then yeah, I mean, our domain can be all real numbers. That's good. And you can kind of see if you put any real number in here and then square it, it's going to turn out to be positive, and then you're going to add 1, it's just going to be more positive. So I can't get that to be 0 in the real number system. Okay. Hopefully that one makes sense. If you have questions on that one, just let me know. All right, now G and H, 2 different families, linear function, quadratic function. And, oh, I'm sorry, actually before we do G and H, let's answer the question down below here. When determining the domain of a rational function, what must be excluded? And again, if you want to put in real number there, that would probably be right. So any number that would make the denominator 0. Okay, very nice. So those 2 families come up a lot. We'll be taking a look at those over the course of this semester here. So notice the conditions on the square root functions and then the rational functions up here. All right, now guys, let's go get the linear and the quadratic and then move on to the graphing calculator piece. So think about domain with just a nice linear function here. My function rules tell us to just take the input, multiply it by 2, and then add 3. Are there any restrictions on doing that? Is there any number I can't multiply by 2 and then add 3 on? No, I don't see any restrictions at all. No conditions to doing that. I can do that on any real number. And so as a result, of course, the domain is all real numbers. No conditions prohibit us from doing it, and so as a result, domain all reals. And then last one here, function b, and it basically says square the inputs and add the inputs and then add 1. And are there any restrictions to doing that? No, I mean, I don't see any. I can square any number, of course, and I can add any number, of course, and then I can add 1. There's nothing that prevents us from doing that. Okay, so we've got a nice little set going right up there. And we'll be looking at a variety of families of functions there, and this just kind of gets us introduced to that. All righty. Let's do some more work now. I'm kind of picking up the calculator and working that out. So if you look at example 2, it does say use a graphing calculator to determine the domain and range. And in this particular case, remember, domain, inputs. Think x, and when we look at the graph, think horizontally. That's the key. So domain, think horizontally. Range, remember, outputs. Think y, think vertically. And so I'll try to represent this as best as possible on my board here. If you have questions along the way with some of these, please don't hesitate to ask. So let's try this out a little bit. Let's see what you guys think. And again, see if I can give a nice visual description up here. We'll give it a try. So let's go for it. Letter A says f of x equals x squared minus 4. So just a nice simple quadratic to get us started here. And everyone, if you can grab your calculator, please, and just go to the y equals and type in x squared and then minus 4. And when you do get an opportunity, please hit zoom at the top and then number 6. That would be just our nice standard window right there. And we end up getting this nice parabola, as you can see. So you are going to have to extrapolate a little bit beyond the window that you see here and think about what's going on with the graph off the window. But from there, basically, we're just going to decide what's going on horizontally with this graph and what's going on vertically with this graph. So horizontally, remember, kind of think about that x right there, sort of relay the graph to that x-axis. And then when we talk range, kind of think about y there, so think about it vertically. Well, here's what I would ask. As we move along the graph, and I do this myself, as I just kind of get used to the graph, just kind of think about it. I go back and forth on it. And as you can kind of see, I'm going to go back and forth on this graph. I'm going to move to the left on the graph, and I'm going to move to the right on the graph. And I guess I would ask you this. Does the graph continue to go to the left forever and ever and ever? Are there any stopping points? Are there any jumps over anything? Can I extrapolate? And I hope everyone's okay with that. Let me bring this back up. That this graph will just continue to go to the left forever and ever and ever. Okay, no stopping points, no breaks. And as you can see, I'm going continuously here. And as I move to the right, same idea. It seems like it's just going to keep going to the right forever and ever and ever. It's never going to stop. And they're never going to jump over anything. And so as a result, as I move left to right on this graph, it's just going to keep going forever and ever and ever. So long story short, the domain should be all real numbers. Okay, and we kind of just talked about a quadratic. Can I take any x value and square it and then subtract 4? Yeah, of course. There are no restrictions on doing that. Okay, so now the range, though. So range, everybody, think vertically there. Think sort of this piece. And again, I just kind of go back and forth on my graph a little bit. And as I think vertically, up and down, I do see that this is going to keep going up and up forever and ever, by the way. And just kind of going down. Looks like it hits this low point right here and then kind of goes back up. So in terms of going up and down, it seems like the up part goes up forever and ever. But the down part seems like I'm stopping right here. There's a low point here. There is a stopping point going vertically. and then it goes back up. So down, up, down, up. And so it looks like we're basically going from -4 down here. I hope everybody sees that -4 on up from there. And so as a result, in terms of the range, I'm getting anything greater than or equal to -4. It looks like the graph, again, let me go back just one more time, is only represented from -4 on up. Okay, again, if I'm not able to kind of really portray this visually that well for you, please let me know and we can kind of do it together. But that would be the case. All right, let's go on to the next. So I'm going to clear that out. Absolute value of x minus 3. So if you would, everyone, hit the math button for me and move it over one to the right. And there it is right there, absolute value. So let's go ahead and hit that. And x minus 3. And I'll just hit graph at this point and let's get that going. So we'll take a look at these V-shaped graphs over the course of the next few weeks. But as you can see, just sort of coming down up here and there, just like this. All right, so of course, using the graphing calculator, we're going to have to think about what happens horizontally. And hopefully the verbal description is working for you. But as I move along my graph, and I just keep moving, think left to right now. To the left, it's just going to keep going and going and going. To the right, just going to keep going and going and going. It's not going to stop. And I'm not jumping over anything. It's continuous all the way through. So let's go for it. I'm getting a domain, all real numbers. So horizontally, all the way through. Vertically, looks like we have something similar to last time around. So it looks like kind of going down and up. And it looks like here's a low point right here, and the graph is only represented above here. So in terms of the y-axis, only above the 0. And so I see this as kind of looking at it. It stops down here at 0 and then goes back up. So as I move along my graph, low point down where y is 0 and then going back up. And so again, just that's how I would describe that range. Anything bigger than or equivalent to 0. Okay, good. Let's go on to the next. A little more complicated square root function right here. Let's see if we can make this one work. So 9 minus x squared. Everyone, if you don't mind typing it in, that would be great. And I'll hit graph on this. I'm actually going to square this up, and you don't have to do this if you don't want to. If I square this up, it actually should be a semicircle as opposed to, it looked a little stretched there on the original window. But it should be a semicircle, by the way. So we have that piece. And so now I kind of like this one. This is an interesting one. It's sort of a little more closed. But it looks like it's only from here to here. It's not going indefinitely by any means. Stops here, stops here. So back and forth. There's a low point. So there's a left endpoint, I guess I should say. And then going this way, there's a right endpoint. So again, it's really only from here to here. So if you kind of look at it, on the left, it looks like it stops at -3. And as I move to the right, it looks like it stops at +3. It doesn't go to the left of -3, and it doesn't go to the right of +3. It's in between those two values. I hope everybody sees that. Just from here to here. If I think x, it's just from there to there. I hope everyone's cool with that piece. And so as a result, I'm curious if you happen to remember how to write this. This is in between -3 and +3. It's what's called the and compound inequality. So it's greater than or equal to -3 and also less than or equal to 3. And we would write it like this. Okay, good. Well, let's go get the range then. Again, just think vertically now. So in terms of going up and down, you know, kind of down here, this seems to be the low point. So from 0 and then up above, it seems to be a high point right up here, then comes back down, stops. So there's a stopping point right down here when y is 0. There's also a stopping point up here when y is equal to 3. And so as a result, vertically, and I'm just going to use that y-axis as a representation for us, it looks like it just from 0 to 3, 0 to 3 right there. Hope everyone sees that piece. Again, this is going to be a little tough for me to teach kind of from the board here, so please ask as you go through the process and we can talk it through. Sometimes that's helpful. But I see that as the range, just from 0 to 3, inclusive. So I include the or equals there. Okay, good. Let's go try a couple others. Cubics. Let's go get that cubic right there. So x cubed, and hit graph. And there we go. Again, really think what's going on with this graph. Extrapolate beyond the window. And actually, there we go. And so in this case, as it's kind of going down, it's also going to the left. So as I think left to right here, is it going to keep going to the left forever and ever and ever? Yeah. Is it going to keep going to the right forever and ever and ever? Yeah, certainly. Just going to keep going, going, and going. And so as a result, I'm getting a domain of all real numbers. It's never going to stop going to the left, and it's never going to stop going to the right. And if you think, let's do the range here, might as well. Same thing vertically. In fact, I think the vertical one is a little easier to see. But is it going to keep going up and down forever and ever and ever? Is there ever going to be a stopping point going up or down? No. And is there any jump or anything like that? No, it's just continuous all the way through. So I'm hoping you see this one. Looks like domain, all reals, and the range, all reals. Okay. Letter E is a fairly tough one here. Might be able to kind of pull that domain off. We saw these rational functions before. But let's see if we can think about it graphically. So last couple here, and then we'll do our application problem, a little above and beyond. So I'm going to do 1 divided by, and then throw in the x minus 2. Has to be in parentheses there, by the way. Kind of like that piece. And then I'm going to hit graph. Not a great window. Let's see, maybe just changing it up a little bit. Not great, but oh well. If we want, we can change the window. Some of you who have the TI-83s will have this vertical line right here. This is what is called a vertical asymptote. Some of you who have the TI-84s, this line probably does not show up. In fact, that might be easier here if you don't see it. But regardless, this is what's called a hyperbola, and it's tough to tell. I could change the window if we really wanted, but let's see if we can interpret just as is. So if I kind of work left to right, here's what happens on this graph. This graph, by the way, does continue to go forever and ever to the left, so it's going to keep going this way. So back and forth. And what happens on this hyperbola, everybody, is as it kind of comes down this way, it goes down and down and down, but eventually there's a jump over this vertical line, and I pick the graph back up here, and it kind of looks like this. So I'm hoping you're kind of seeing that to some degree. So left to right, let me get that again. Here's what happens left to right. Going from negative infinity, so going all the way to the left, coming over, going, going, going. It's coming down like this. It's going to shoot on down all the way through. And then again, what happens is we get a little jump as I move left to right. It jumps over that vertical line, and I pick the graph up right there, and then it just keeps going and going and going. So tough one to see. But I guess you would kind of look at this and be like, hey, this is a rational function. And I know I can't divide by 0, and so as a result, x can't be 2 because that would make me divide by 0. And that's what's excluded right up here. I know it might be tough to see, but that vertical line is that vertical boundary when x is 2. Now vertically, what happens, again, this continues to come down here forever and ever and ever. What kind of happens is as I'm moving upward, notice the graph starts to plateau vertically. It's getting closer and closer and closer to that x-axis there. Yeah, let's bring that back up. And then what happens, same thing, guys, there's a jump. So I jump over the x-axis and I pick it up here as I go vertically. So this is going to be probably the hardest one to analyze. But basically what happens is I go vertically, and by the way, this keeps going up and up and up. As I go vertically, there's a jump right there. And what you would see is there's a jump over a y value of 0. You can never get a y value of 0 here. So ask about that one if you don't see it. But that one's a little harder, of course. Let's do one more. And then, as I said, let's try just the application piece down below in a moment. So here we go. Let's do 2 and then raise to the x. And I'm going to hit graph one more time there. Let's get that standard window. And so here again, if you're not sure what's going on, you can always trace. Sometimes I have students do that. If you kind of trace it out, if you're not sure what's going on with that graph, notice it does keep going to the left there. That would probably be one of your questions with this one. And notice it does keep going to the left there. Actually, it keeps going to the left forever and ever and ever. So in terms of this piece then, the graph kind of looks like this all the way through. And so as we go left to right, everybody, is it ever stopping or is it ever jumping over something? Nope. It's just going to keep going forever and ever and ever, left and right. So as a result, for these exponential functions, and we'll do a lot of work with exponential functions, by the way, the domain will be always all real numbers. Now the range, it's kind of interesting. If you think vertically here, up and down, looks like up, it's just going to keep going up forever and ever and ever. But coming down like this, everybody, it seems like it's really plateauing. And I guess the question is, do you think that this graph will ever hit that y-axis? Notice I've got a y value here close to 0. As I keep moving to the left, do you think that it will ever actually hit the number 0? No. And so what we have is we have this lower boundary where it's just the graph is just going to be above. And in this case, it's just going to be above 0. So I hope that description kind of works for you and that you saw that translate. That the range is going to be all numbers bigger than 0. Not or equal. Not or equal here. Okay, so again, kind of a tough set to go through. But get some practice on this. Try some on your own and see if it works for you. And let me know how I can help. Let's do just the last one here. Kind of a little above and beyond. Talking basic domain and range is probably to some extent a good review for you. But this one here is probably a little above and beyond, as I mentioned. So let's go for it. Example 3. An open top box is to be constructed from cutting squares from the corners of a rectangular piece of sheet metal and then folding up the resulting flaps. If the rectangular sheet metal is 8 inches by 10 inches, find the domain and range of the volume function in terms of x. All right, interesting. So we're going to write a function for the volume in terms of x, and then talk about its domain and range from there. Well, this is a fairly common problem at this level. We'll probably see this in a couple different contexts before we're all said and done. So we're going to look at this one kind of for the first time, just in terms of domain and range. So everyone, if you would, let's start this out. If you can give me a 10 by 8 piece of sheet metal, so something like that would do. And the way this is going to work, if you haven't seen this scenario before, is we're basically going to go ahead and cut the squares out from each corner. Now the size of the square can vary. They do have to all be the same, at least. That has to be clear. But the size of that square right there can change. And how it changes is going to affect our box. And so if it's something that changes, we're going to label it with a variable. And so basically the length of one of those squares right there is going to be x. So that is our situation at hand. And we're going to cut out those 4 squares from each of the 4 corners. And we're going to get a particular type of 2-dimensional figure. Now, I can't draw to save my life. But if we were to cut them out, you would probably get something like this, give or take. Yikes, that's trouble. Okay, but you're going to have to use your imagination, and hopefully you're going to draw better than I draw. But basically, we would cut out the 4 corners. There they would go. And you would fold up each of the 4 flaps. So picture this now 3-dimensionally, if you would. This folds up, this folds up, this folds up, and this folds up right there. And they all fold up and they meet, and they form what is called an open top box. And so now, envision that open top box. And let's talk about the length and the width and the height of that box. Okay, so let's see what we have going. Now the length of the box, I'm hoping you would see, would be from here to here essentially. Okay? So if you kind of look at this, we're going to do this all in terms of x. The length of the box is from here to here. Now if you look at our box, our sheet metal, we started with 10, and then we cut out an x from here, and we cut out an x from here. When we cut out those 2 x's, that gives us really what's remaining along that length, essentially. That's the length of our box. So we started with 10, and I took away an x from each side. And so what the length would be, I'm hoping you would see, is 10 minus 2x. So that would be from here to here. If you can envision that 3-dimensional box, there's your length. Now the width, everybody, is going to be from here to here. Now again, ignore my poor drawing, but basically that would be the case, from here to here. We started with 8. That was 8 if you remember, but now we took away x from here, and we took away x from here. So the width is going to be 8 minus 2x. Okay, good. Now the height, this is the fascinating one. The height, remember you're folding up the flap, so think about that flap, and now think three-dimensionally. Think about this coming off your paper at you, basically. But basically, I'm hoping you would see that the height would be this flap right here. And that flap is actually something we labeled, that's x. So as you can hopefully see, there it is. And so we have the length times the width times the height, all in terms of x. As x changes, the volume changes. And we'll kind of get into maybe that particular context maybe a little later on this semester. For right now, what I'd like to do is type this in the calculator and go ahead and come up with a suitable domain and range. Okay, so a couple things to note. Oop. Let's bring that back up there. Okay, so here we go. Everyone, if you would, go to the y equals, and let's type it in. 10 minus the 2x. 8 minus the 2x, and then x. Now, it should be noted this is what's called a cubic function. And cubic functions, in reality, have a domain of all real numbers. So it's very tempting to just say, hey, wait a minute, domain, and in fact the range too, that the domain and range are all real numbers here. Unfortunately, what I'm looking for is not just the basic mathematics here for the domain and range, but a suitable domain and range for this application right over here. What makes sense with the problem, not what works in the context of just this function. Okay, well guys, hit window for me if you would. And I guess we would all probably start out with the fact that, you know what, you're cutting something out there. So you can't cut out a negative. So we know that in terms of our domain, it can't be negative. So why don't we start out at 0. Go to 10 for right now if you don't mind. And in the volume will be our output here. So remember, it's volume in terms of x. Volume can't be negative. So let's do 0 here. And then this is always a tough one to do. If you ever have issues with this y max is always the hardest thing to get. I like playing around with it a little bit. Let's start with 100 and see what happens. Okay, guys, I'm going to hit graph. You're going to do the same. And that's good. Actually, we've got something nice here. So notice what happens. And by the way, this graph, if we were to really follow it to its natural conclusion, it does go down here forever and ever and ever. So it comes up, peaks right there, comes down a little bit below, and then back up again. So again, you would follow this and be like, oh, wait a minute, domain, range, all real numbers, of course. And you would be right, except that's not what I want here. So what makes sense with the problem? Well, I already gave part of it away. I already said that x can't be negative. So you know you have to cut out something. And you know that there is a limit to what you can cut out here. Think about that for a second, and we'll relate it to the graph. What is the maximum that you can cut out from each corner here? And think about that for a moment. Can I cut out 1 unit? Can I cut out 2 units? Can I cut out 3? Can I cut out 4? Can I cut out 5 units? Can I cut out 6? What makes sense? And I'm hoping you would see, especially as you look at the smaller length right here, I guess we would call this the width of our rectangle, I can't really cut out too much here. I can cut out maybe up to 4 here and maybe up to 4 here, but if I cut out 4 or more, I don't have anything left for a box, do I? So it looks to me like I can do anything up to, but not including 4. And take a look at the graph if you get an opportunity to see this. So here's the 0 piece, right? I have to cut out something. So I'm cutting out something and I'm getting a volume, cutting out something and getting a volume. But what happens when I try to cut out 4 units? I end up getting no volume because there's no box. And then what happens is it goes down below. And this stuff is just all extraneous because can I cut out 5, 6, 7, 8 units? No. Because look, the fact is I only have 8 on this whole thing and I've got to cut out from the top and bottom here. So I know it's tough to see, but I kind of like this as our domain right there. That's it. I can't cut out up to 4. So anyway, that would be your domain. From 0 to 4, not inclusive. All right, cool. Now the range. Remember, the range would be all of the volumes that you can get from cutting out the squares. And in this case, everybody, now I'm kind of focused not on the entire graph, but just on this piece of the graph right here. And if I think vertically, it looks like the volume goes up, goes up, goes up. There is a high point, and then the volume comes back down. And so you can see there's a stopping value, essentially. The graph stops when I move vertically up here and then comes back down. So as I look at this, I know that the lower end is going to be 0. So obviously, guys, we have to get a volume bigger than 0. But there is an upper end to that. There is a maximum volume. We'll be talking about maximizing and minimizing functions over the course of the semester. In this case, there is a maximum volume right up there. I'm not sure if you remember how to do this to find a max, but let's go ahead and go through it once and then we'll wrap this up. If you can hit the second button for me and then trace. And this menu we'll do a lot with over the course of the semester. Go to maximum. And notice it sort of gives you a left bound there. What I do is I just kind of scroll on over, try to scroll a little faster. You want to scroll to the left of where your maximum would be. So I come over to the left of it. Anywhere to the left is fine, and you hit enter. Then if you would, come to the right of it and hit enter, and then hit enter one last time. And notice what it gave you. It told you how much to cut out from each corner, and it gave you the best volume possible, the maximum. So about 52.51, give or take, in there. And so up to, and including, because that was the max, about 52.51 cubic inches. So a good, fascinating problem there. It's well beyond just looking at a graph and interpreting, but it's understanding what makes sense in the context of a good application problem right here. So I kind of like that. You'll probably try one or two of those. What makes sense? Think about that piece. Okay, everyone, be great to get just some practice on domain and range. And please let me know if there's anything I can help with. Kind of talking things through with this may be a little easier than seeing it from just the video. So thanks for listening, of course, and don't hesitate to ask questions.